Today, we're going to pull back the curtain on the world of microchip design. We're looking at a quiet, kind of invisible innovation that makes pretty much everything in our digital lives faster, cheaper, and way more reliable. It's a revolution in code that you've never actually seen, but trust me, you use it every single day. Let's dive in.
So let me ask you this. It sounds like a trick question, right? But for the engineers who design the chips in your phone, your car, your laptop, this is what they do all day. Just try to imagine testing a city with billions of tiny moving parts, checking every single street and connection before a single foundation is ever poured. I mean, how on earth do they even begin to do that?
Well, the answer is they do it all in the virtual world. Before a single piece of silicon is ever touched, that chip design has to go through this incredibly intense series of tests. Think of it like a full-blown digital dress rehearsal, making sure every single actor hits their mark for a perfect opening night.
This whole process has a name. It's called chip verification. What engineers do is they build a digital twin of the chip, and then they just throw millions of simulations at it. They're stress testing every single function to find bugs before those bugs become really expensive real-world problems. Every virtual circuit, every transistor gets pushed to its absolute limit.
But here's the thing. You can't just run millions of tests randomly. That would be chaos. It's actually a highly choreographed dance. And to coordinate it, you need a master plan. Engineers use these scripts they call virtual sequences. These scripts are kind of like the conductor of a massive orchestra, telling every little component exactly what to do and precisely when to do it.
And that brings us right to the heart of the problem we're exploring. For years, the way they managed these absolutely critical test scripts was, well, it was powerful, for sure, but it was also incredibly fragile.
The classic tool for this is called the virtual sequencer. The best way to think about it is like an old-school physical bulletin board in an office. It's got all the information you need, directions to find every test coordinator. But here's the catch. To find the right directions, you have to know the exact spot on the board where they're pinned down. No searching allowed.
So here's how this delicate process actually worked. An engineer would literally write down the exact address. We call this the hard-coded path to a specific test coordinator. And the test would follow that path, no problem. But what happens when the chip design changes? Which, by the way, it always does. Components get moved, the whole layout shifts, and bam, that address is suddenly wrong. The path is broken. The test fails.
In the super fast-paced world of chip design, where things are constantly being updated and changed, this isn't just a small inconvenience. Oh no, it spirals into a complete and total maintenance nightmare really fast.
And hey, you don't have to take my word for it. In their research paper on this, engineers Clifford E. Cummins and Mark Glasser just said it perfectly. This whole system relying on these fixed paths quickly becomes, and I'm quoting here, a maintenance headache. Every single time the design changes, engineers have to go on this massive hunt to find and fix all these broken paths. It's frustrating, and it's a huge source of bugs.
At its core, this whole system was committing a major design sin. It violates a really important engineering principle called hierarchical independence. The idea is simple. A component shouldn't need to know its exact street address in the grand scheme of things to do its job. By forcing it to know its location, the old method made every part rigid, fragile, and almost impossible to reuse in other projects. This slide just lays it out so clearly. On the left, you've got the old way, this tangled, rigid mess that breaks if you so much as look at it funny. And on the right, you have the goal, a system that's flexible, reusable, and just works. The challenge for engineers was pretty obvious. How do you get from that mess on the left to that dream on the right? And that brings us to the hero of our story today, a simple, really elegant solution that just completely changes the game. It's called the sequencer container.
The big breakthrough came from asking a question that is, honestly, almost ridiculously simple. Instead of needing to know a component's exact physical address, what if you could just ask for it by name?
And that is precisely what the sequencer container does. It's a new kind of data structure that works like a central registry. So instead of that old messy bulletin board, it's like a modern, searchable company directory on your computer. You don't care where someone's desk is, you just type in their name, hit enter, and you're connected. It's that simple. The benefits were huge, and they were immediate. All of a sudden, poof, no more hard-coded paths to break. The system finally achieved that critical goal of hierarchical independence. The test environments became genuinely reusable and super easy to maintain, which in turn wiped out a massive category of bugs that used to drive engineers crazy.
What's really cool is that this new solution isn't a one-size-fits-all thing. It actually comes in 2 different flavors, each one designed for a specific kind of project. You've got the sequencer pool and the sequencer aggregator.
All right, first up is the sequencer pool. It's what's called a singleton, which is just a fancy way of saying there's one single global directory for the entire project. It's absolutely perfect for smaller designs, where it's pretty easy to give every component a unique name. Then, for the giant, really complex chips, you've got the sequencer aggregator. This one lets engineers create multiple, separate directories, so different teams can work on their own parts of the chip without worrying about their component names bumping into each other. It's all about having the right tool for the job.
Okay, so I know we've been way down in the engineering weeds, but let's zoom out for a second. Why does a small-sounding change like this actually matter in the real world?
It matters because of this. This is a huge statistic. A 2022 study found that the single biggest thing that causes these massive chip projects to fall behind schedule is the time spent debugging. It's not the complexity, it's not manufacturing, it's just hunting for and fixing mistakes.
And that's really the big takeaway here. Better tools, like the sequencer container, they're not just about writing tidier code. No, they are a direct assault on the #1 cause of delays in the multi-billion-dollar semiconductor industry. By just preventing this whole class of bugs from ever even happening, they make developing new technology faster, cheaper, and way more reliable for every one of us.
It really makes you think, doesn't it? We just looked at one really elegant solution to one very specific, tricky problem. It just leaves you wondering, what other invisible breakthroughs, what other clever ideas are quietly humming away behind the scenes, making this complex digital world of ours even possible?